Hi, my name is Chris Gator. I'm the Design Centre Manager for Micrel Semiconductor in Livingston, Scotland. Today I'd like to introduce you to one of Micrel's newest regulator technologies, which we're calling the ripple blocker. The ripple blocker is essentially a power filter that can be configured as a load switch with a current limit, or a power filter so the output follows the input, or it can be configured as a high performance LDO. The part is unique in that it offers fantastic power supply rejection up to 10 megahertz, and it only requires a very low voltage drop. It also comes in a very small package, chip scale package, 0.88 millimeter CSP, and also in a thin MLF at 1.2 by 1.6. It only requires a very small ceramic output capacitor and a very small input capacitor, 0201, 1 microfarad ceramic.
Again, my name's Chris Gator. I'm the Design Centre Manager for Micrel Semiconductor in Livingston, Scotland, and I've been there since 2000. Micrel, as you know, has a long history producing switchers and linear regulators. Our switchers are typically used when system efficiency is important, and linear regulators when low noise or low cost is important. More and more our customers are asking for us for ways to help them optimize their system performance, reduce board space and reduce cost. So in response, Micrel would like today to introduce you to our newest regulator technology, which we're calling the ripple blocker. So who needs a noiseless supply? The obvious answer is everybody would like a noiseless supply. But today I'm talking more specifically about coherent noise, the kind of noise that's generated from a switcher, typically in the 50 kilohertz to sort of 5 megahertz range. And that noise can mix to all other places in your system to a bad effect. The noise can appear on the DC power supply, or it can parasitically couple through a PCB. CMOS imaging sensors require low noise. If there's noise on the charge amplifier or on the ADC, it can affect the dynamic range of the system or the sensitivity, especially in low light conditions. Transducer circuits all need low noise. The better the noise, the better the measurement. GPS systems, they are notoriously sensitive to all sorts of noise. Noise will mix in weird and wonderful ways, and if it appears on the L1 or L2 carrier frequencies or gets modulated down into the IF band, it can dramatically affect system acquisition, system tracking performance. And then cellular and RF products all rely on very accurate timing references, and the clocks in these systems generally developed from a crystal oscillator and a phase lock loop. So in the phase lock loop, if noise appears on the charge pump or on the VCO, that will manifest itself as timing jitter, and the worse the timing jitter, the worse the bit error rate. So in fact, many of our customers today are asking for fixed frequency switchers or switchers with a forced sync function, where they can lock our DC-DC to their own system clock to avoid any noise appearing on an unwanted frequency. So what does a ripple blocker do? A picture's worth 1,000 words. So what we see here on the left is a Micrel MIC 23155 hyper light load switcher, and we're just really using this for demonstration purposes. It has 5 volts in and 3 volts out. It's operating at 630 kilohertz in discontinuous mode. What we have on the right is the first member of our new ripple blocker family, which is the MIC 94300. It's a ripple blocker configured as a voltage follower, so it's like a power filter. Up here on the plot on the left, you can see 25 millivolts peak-to-peak ripple coming out of the DC-DC. It's not normally that high, but for the demo board it's running discontinuous mode, so the ripple is quite high in this particular configuration. You can see the spectral content here. It's producing spurs over a broad range of frequencies. I think this is up to 5 megahertz here. On the right, you can see what the ripple blocker does. The ripple blocker, in essence, is a power filter, but the technology can be easily configured through metal masks to act as a current limited switch, it could act as a power filter, and it can also act as a high-performance LDO. The unique thing about it compared to other products is that it offers excellent power supply rejection up to 10 megahertz, so you can clean up DC-DC ripple. Conventional LDOs have trouble at these kind of frequencies when you get up to multi-megahertz cleaning up DC-DC ripple. That's really what the ripple blocker is targeted at. The other unique thing about it is it offers that power supply rejection with a very low voltage drop. So that improves system efficiency and extends battery life. It does it in a very small package, 0.88 millimeter CSP, and it only requires 1 microfarad input and output caps. And the particular ones we're using in the demo board are 0201, so they're very small. It's integrated in standard CMOS technology, so the technology is very portable and we can apply it to new applications as they appear, and we're hoping that will open up some new markets. There are other ways to reduce this kind of ripple. You could use a DC-DC that was driven from a spread spectrum clock, but that it will reduce these spurs, but it does also tend to lift up the noise floor because it smears the energy from one band out to a wider band. The other way you can do it, obviously, is to use big passive power LC filters, but they tend to be big and expensive. In fact, for the ultimate suppression, you could use a ripple blocker technology and then follow it with a very small LC, and that would give you the best of both worlds. Here we see a block diagram of the 94300. It's a 4-pin device: input, output, enable, and ground. The first member of the family is a follower, so it's like a power filter where the output just follows the input by a fixed voltage drop. That voltage drop is set by a reference, an onboard reference, which is VIN referred. So it just gives you a fixed drop, in this particular case 170 millivolts down from supply. We follow it with a third order Salon and Key analog filter with a passband of 2 kilohertz. The value of that reference is chosen to meet two things. We use an NMOS output stage, a power FET, as a follower. So we have to keep that device just into the active region, which is the optimum position for best power supply rejection for a given voltage drop. The other thing is we need additional headroom to take care of any ripple at the input, because if you're operating that device just at the triode region, any perturbation on the input is going to upset your power supply rejection. So you have to have a drop here big enough to keep this in the active region and also to accommodate the kind of ripple you need. So this particular device we've introduced has 170 millivolts, and it's good for blocking up to 50 millivolts of noise. We've chosen an NMOS output stage configured as a follower because of the natural suppression that gives us. This reference is set to hold that always just into the active region. And by doing that alone, we can get about 25 dBs of flat band suppression, just from the fact this is acting as a source follower. That suppression continues up in frequency until you get an output filter here. So the capacitor sits on this output here, and then the GM and then the C of that produces a output filtering action. So your flat band suppression actually improves, and that will continue improving up until the parasitics ESL of the output capacitor starts to resonate with the capacitance, and then your PSR will start degrading again.
I'd like to show you a demo board here today. Here we have, on the left, we have a Micrel 23155 hyper light load switcher operating at 630 kilohertz, and it's operating in discontinuous mode. So it's producing a waveform over, you can see over here, 25 millivolts, peak-to-peak ripple in a sawtooth. You can see what the ripple blocker does below it here. It's really eliminating all that ripple. So essentially the ripple blocker is intended to eliminate ripple produced by a DC-DC converter. Perhaps the best way to look at it is to look at the spectral plot of the before and after the ripple blocker. On the right here we see a plot. Because it's operating at 630 kilohertz in discontinuous mode, the waveform is sawtooth in nature. So it's producing energy content at all of the harmonics. We can see the fundamental here at 630 kilohertz, and the marker up here is minus 20, so the fundamental here is about minus 24 dBm. If we then look at the output of the ripple blocker, you can see that it's done a good job of eliminating all of the ripple from the DC-DC. The noise floor here is down at minus 90 to 95 dBm, which means that the ripple blocker is suppressing noise in excess of 60 dBs from very low frequencies all the way up to 10 megahertz. I've now moved to the output of the high-performance LDO, and again you can see the ripple blocker has eliminated all of the DC-DC switching content. We're down here with, at low frequencies, we're getting in excess of 80 dBs of rejection from the LDO, and at high frequencies between 40 kilohertz and 4 megahertz, we're getting in excess of 55 dBs rejection. The ripple blocker is unique in that it can offer this kind of rejection with a very low requirement for headroom. There are there's really, well, three chips of interest. This one here is the DC-DC converter, and over here we have two ripple blockers. On the top we've got a ripple blocker which is configured as a voltage follower. That acts like a power filter, and below it we have the other version of the ripple blocker family, which is a high performance LDO.